In this example, we're going to take a look at this equation here, y equals the natural log of x raised to the power of x, and we're going to use logarithmic differentiation to find its derivative. So if you would like to pause the video and go ahead and give this a go real quick, and then come on back and we'll work it together. Okay, so what's so nice about logarithmic differentiation is that it looks like we have an x in the base, but we also have an x in the exponent, which seems like it's going to be a little bit difficult to take this derivative. So what we're going to do first is start by taking the natural log of both sides of this equation in an effort to kind of rewrite this right side in a much simpler way. So we have the natural log of y equals the natural log of, and we have, well, the natural log is the base here raised to the power of x. This is nice because this exponent that was an x, we can now use the properties of log and we can bring that out front as a coefficient. So we have the natural log of y equals x times the natural log of the natural log of x. Okay, so now we have a nice product rule instead of something much nastier. Okay, so let's go ahead and differentiate both sides of this equation. And you'll see I have included the differentiation rule for the natural log of some function u. And this rule is one of many rules you can find typically in the front cover of your calculus book. Okay, so let's go ahead and differentiate. So we have the natural log of y, so its derivative is y prime over y, equals, and it looks like we're going to use the product rule here. So the derivative of the first is 1 times the second, so we just bring that down, plus the first times the derivative of the second. Okay, so the derivative of this, we have the natural log of, and this function inside here, so the numerator will be the derivative of the inside, so that's 1 over x over that ln of x. Okay, so here's where we are right now. And it looks like we can clean this up a little bit. We have x times 1 over x, so those will cancel, leaving me with just a 1 in the numerator. So rewriting this real quick looks like this. It's the natural log of x plus 1 over the natural log of x. All right. So remember, though, we're trying to solve for this y prime, because that's kind of our dy dx. So we're going to go ahead and multiply both sides of this equation by y. So on the left side, those cancel, and I'm left with just y prime, which is nice. But here we have this y that we're multiplying through. But from our original definition here, or our original equation, what was y? Well, it was the natural log of x raised to the power of x. So I'm going to go ahead and exchange this y for that natural log of x raised to the power of x. And now we can go ahead and distribute to here and here for this multiplication. So what it looks like I'm going to have now is the natural log of x raised to the power of x times the natural log of x plus, then it looks like the natural log of x raised to the power of x over the natural log of x. And of course you could leave it this way. This is one good way to do this. There's lots of other ways we could write this or try to clean this up a little bit more. One such way, you can look at a term like this and you realize that this could really be rewritten as the natural log of x raised to the power of x over the natural log of x raised to the power of 1. You'll notice they have the same bases. So we could say it's the natural log of x raised to the power of x minus 1 for this term. But again, sometimes we can spend a lot of time simplifying or coming up with various other ways to rewrite these expressions. But this is a fine way right here. And if you want to go to more effort, then certainly go for it. But anyway, so we have used logarithmic differentiation. We had y equals, and then the natural log of x raised to the power of x. And in our process, this is what we came up with. Y prime equals, and then we have this expression.